This would, of course, refer to the pure, if you guys see here of the pure liquid, so I might stick an L on there if I want, but it's understood. So often, we approximate the standard state for the solvent as just equal to the pure component vapor pressure. So let's note that. And if we make that approximation and put it up here, then we get this expression, and if I assume I have an ideal mixture of ideal gases for the vapor over here, I have just the partial pressure, Y1P, and we get what we've been working with all along, namely modified Raoult's law. So you see modified Raoult's law is just a subset of our modified Lewis and Randall Rule. But we now have the whole situation with respect to solutions described, the way we handle it, with all of the terms having been introduced and defined.
So the fugacity of 2 in the liquid phase, why is that equal to Y1P? I thought that was for the fugacity in the vapor phase.
I'm equating it to the fugacity because what we referred to as modified Raoult's law. All right,
Oh, because the equilibrium.
Yeah.
Okay, I got it.
Yeah.
That's easy. Yeah. Okay, makes sense.
But there's one issue that's left here that I want to describe, and that is how we describe the composition of these solutions, particularly dilute solutions, because the use of mole fraction is fairly awkward for at least a couple of reasons. One of them is that the numbers tend to be very small. So we've got x2 equal 0.00 something like that. So it would be handier to have numbers that are bigger than that, so we're not holding all of those decimal places. But another more important reason is that when we're dealing with dilute solutions, we often have multiple solutes. So we'll have not only a component 2, but we'll have a component 3 and a 4 and so on. And we'd like to have some measure of composition where the presence of one of the solids doesn't affect the value of the concentration of the others. And with mole fractions, that would be the case. In other words, if I had a third component, in other words, another solute in there, that would start, its presence would influence the mole fraction for component 2. Anyway, we'll see how that all sorts itself out here. So let's look at the issue here of the composition of dilute solutions and how we describe it. Let me write the quantities out in words here. We've been using mole fraction. Moles of 2 over total moles. But a couple of other common measures that we have for this concentration of a solid would be molarity. That's sometimes also referred to just as concentration. But the symbol that's used for that is a capital C2, and that's equal to moles of 2 over a liter of solution. This is one that I particularly don't like to use because now we're involving ourselves with a liter, so whatever the liter of solution is going to depend on what the density is, which depends in turn on what the temperature is. Anyway, you will often see Henry's law written here with respect to molarity. Another one is mass concentration. This is an important one for polymer solutions. So that's a lowercase c here. And that's grams of 2 per liter of solution. And then the last really important one that I want to get to is a different type of animal, and that's the molality. We use a lowercase m for that, and that's equal to moles of 2 per kilogram of solvent. It's a different animal than the other three because it has in the denominator something that just refers to the solvent all by itself, not to the solution. Now, when we're down in the Henry's Law range, all of these entities are linearly related to one another. If we get above Henry's Law range, then that linearity, that direct linearity disappears. It can be worked out, but we're interested in the Henry's Law range, so let's work it out for a number of these cases. How much space have I got here? Let's note here that for this capital one, M1 is equal to molecular weight of the solvent. M2 is the molecular weight of the solute, and so forth. If I had more than one solute, then it would be M3 and so on. So I'm going to need that. So let's systematically go through and relate all of these quantities back to the mole fraction. In the case where Henry's Law is valid, that is, we've got sufficiently dilute solution. So C2 here is, and here's where I really wish I had a board, but I've got a limited space here to work. So we'll see how it goes. We got, this is moles of 2 per moles of solution times moles of solution over liter of solution. So this is approximately, as the first factor here is just the mole fraction, and the moles of solution is essentially equal for ordinary solutions, or solutions of ordinary molecules, small molecules, well approximated as just the moles of the solvent. By liters of the solvent here. And I can write this out now as X2 times, there's the density of the solvent, which is in cubic centimeters, in grams per cubic centimeter. So this is rho then times 1,000 over M1. And I can write that. And here is X2 times 1,000 times the density in grams per cubic centimeter over the molecular weight. So let's just remind ourselves of that. This is in units of grams per cubic centimeter. So we see the proportionality between the molarity and the mole fraction here is 1,000 rho 1 over M1. What is the next one? Mass concentration. So that's little c2. What we notice right away is that that's grams of 2 over a liter of solution, so that's just going to be equal to big C2 times M2. So we can just refer to the equation above to get that relationship. The proportionality factor there would be the same as I've got here above times M2. And may be evident why this is a useful unit when we're dealing with solutions of polymers. But the really important one that I want to emphasize here is the molality, that's little m2. Let's write it out, that's moles of 2 over moles of solution over kilogram of 1, that's of our solvent. So under dilute solution conditions, that's going to be x2 here times, this is effectively moles of solution is approximately just moles of our solvent 1 over kilograms of 1. So I can write that out. I think I've got enough room here. This is just going to be x2 times 1,000 over m1. So that's the most important relationship that we got out of it, right here. That little m2 is approximately equal to x2 times 1,000 over the molecular weight here of the solvent. And more often than not, you're going to see Henry's law expressed on the molality scale. Which is the way I think it really should be done. And if we write that, then we've got the fugacity here of the solute in the liquid is equal to the molality times a Henry's constant. But we now have to remind ourselves that that's a Henry's constant based on the molality scale for our composition. Or for the modified one, we can just do the same thing. Where this is now, we're getting a lot of decoration on this, but that is the activity coefficient based on the molality scale, or the molality-based Henry's law. It's evident that we can relate the two values of the Henry's constant, that is this one based on the molality scale, back to the original one just by writing out the two expressions, or 2L. And if I write it out here, then I can express that as it's evident that from equating these two, that Henry's coefficient here based on the molality scale is just equal to m1 over 1,000 times the Henry's law based on the mole fraction. So if we wanted to work with the molality scale with the Henry's law table that I've given you, then we could make this correction and we would have it. Yeah.
I'm sorry, is that a big M or a little m in the very end?
No, you have to tell me which place. Here?
Yeah, at the very, very end.
Yeah, that's a big M.
Okay, that's what I thought.
So that is, it's hard to write really bad enough sitting down than standing up. Look better? Yeah,
And that refers to molecular weight of the solvent?
yes,
Okay.
yep. So what we've introduced here is, if I can just put a circle around it here, molality-based standard state. And when people talk about the solute standard state without any further description, they usually are referring to this one. So let's take a quick look at a diagram here that may illustrate exactly what that is. You would be able to figure it out, but let's diagram it. So we're going to have a similar situation. We're going to obey Henry's law at low and left modalities now. So let's say it's good up here, and then it starts, the actual data start to deviate away. And here's Henry's law extrapolated out here in terms of molality. And what we find is when this gets to exactly 1, in other words, unit molality, that defines the situation. So this is so the standard state, the solute standard state on the molality scale is the fugacity of a hypothetical Henry's law solution at unit molality. In other words, when the molality is equal to 1. So let's write it out. There it is written out in words for you. Now, it's of some interest, we may get into it, we may not. After the midterm, when we're studying chemical reactions, to study chemical reactions in dilute solutions. And they are more often than not described in terms of the molality of the reactants that are present in dilute solution. And that's going to be important to know what the standard state is for that description. And we just refer to it as a solute standard state, and it usually is referred to in terms of molality, as I've given you here. So I think this is enough on our dilute solutions, which kind of ends it for today, unless you have some questions, because our next big topic, which we won't really get into until after the midterm, is going to be chemical reaction equilibria. Yeah.
Yes, for the volume of a solvent at infinitely small quantities at V21 infinity.
Yeah.
How would I find that?
Yeah, that's a tough one. You generally aren't going to be able to find it.
Okay.
But what you can do is get a rough estimate for it. And in desperation, one thing you can do is just go look up what the critical point molar volume is for that material. Most tables have it. Unfortunately, Koretsky doesn't give you that in the critical state properties. But it's going to be a liquid-like molar volume, even though the solute you're dealing with is more often than not a gas. So this is now the liquid, the hypothetical liquid state molar volume. So when that gas dissolves in a liquid, it has a partial molar volume that is liquid-like in its size.
Thank you.
That's a good question, Rudy. There aren't many data on it. Yeah.
I have a question on azeotropes from last week.
Yeah.
Like if you have that system of ethanol and water or like cooling, there's like a certain temperature where you have an azeotrope.
Right.
How much does that change if you alter the pressure?
Yeah, good question. It does change, but not a lot. So this is a problem if you're trying to operate a separation process. An azeotrope is terrible because you can't get past it. Let's say you want to purify one of the components, you can have stage after stage after stage, and you're not going to get beyond the azeotrope. So people figure out ways to break the azeotrope. And one of the ways is to modify the pressure. But it turns out that quite often you have to modify it so much that it's not practical.
There's no like every system doesn't behave the same way.
Say again?
Like every system doesn't change in the same way.
Correct. But it's a general rule that modifying the azeotrope by modifying pressure, it doesn't get modified very much. By the way, that's a very interesting thing, but that's for a graduate class. We could derive that. You have everything actually you need to know to be able to derive it. It would be challenging. So how do you suppose they do break azeotropes?
Well, I was gonna say like you add a third component.
That's exactly right. That's the most common one used, and that's actually called extractive distillation, where you add a third component will change the relative volatilities of the other components sufficiently that you break the azeotrope. Any other thing for discussion before we break up for today? Bring questions as well for Friday, because all we've got to do Friday is going over the homework, and there's no quiz. And so that's going to leave some extra time, and I don't want to start new material, so if you have other questions, that would be a good time for it.